Welcome to the Ecological Continuity Trust webinar series. First of all, a little bit of housekeeping. If I can ask you to keep your microphone muted during the talk, and if you're also able to turn off video, that just saves us a bit of bandwidth. I'm very pleased to welcome today Mike Moorcroft from Natural England. Mike's a founding member of the Ecological Continuity Trust, so we're particularly pleased to have him back talking to us. Mike worked with the Ecological Continuity Trust for 10 years before he stepped back for his new role in climate change with the IPCC. Many of you will know Mike works at Natural England, and he's going to talk to us about climate change and long-term ecological field experiments. Over to you, Mike.
Great, thanks, Carly. Yes, it's brilliant to be with you. And I'm just going to share my screen. So, climate change and long-term ecological field experiments. And this is where we're going. So, after a little introduction, then we'll move on to think about climate change impacts and then move on to what we do about those impacts in terms of climate change adaptation and mitigation. So, as Carly's alluded to, I have history with the Ecological Continuity Trust. I was one of the founding trustees, and that reflected my own concerns about the importance of long-term experiments alongside long-term monitoring, and monitoring and experiment will both feature today. There's me in Wytham Woods doing some long-term monitoring, and there's drought experiment on upper seeds at Wytham, looking at the effects of climate change on grasslands. So I have history, but a lot of my work these days is not hands-on with long-term experiments. It's still very much in the science field, and I will tell you a bit about my current work as we go along. But this is just a recent picture of me at 27 in Egypt, talking about some of the latest work from the Intergovernmental Panel on Climate Change, the IPCC, which played a lead role in. And I'm just going to zoom in on that slide that you can see being shown there, which is a statement we made at the end of our climate change impacts and adaptation report, that maintaining the resilience of biodiversity and ecosystem services at a global scale depends on the effective and equitable conservation of approximately 30 to 50% of Earth's land, freshwater and ocean areas, including currently near natural ecosystems. Something we could say with high confidence. Because of multiple lines of evidence. And one of the themes that will come out as we go along is that actually, to build up the big picture, you need to understand all different sorts of evidence of which monitoring, experiment are a part. They need to be seen in a bigger perspective to be able to really inform the big decisions and the big challenges that we face. So my report was the one in the middle there. These are all available to download. Report on the physical science basis of climate change, a report on the impacts, adaptation and vulnerability to climate change. That's my one in the middle, and then around mitigation of climate change on the right. And you'll see I've got a lot of slides from those reports. They're very much in my mind, particularly our one, but I will also intersperse it with Natural England work and others as well as we go along. But you'll find I will not be giving a lot of detailed information about particular experiments and the sort of thing that a lot of ECT work concerns itself with. So bear with me, this is seeing the big picture and where long-term experiments fit in. So let's start with the impacts then of climate change on biodiversity and ecosystems. And these are some of the real headline global findings from that report published earlier this year. So many observed changes in the ranges, phenology, physiology and morphology of terrestrial freshwater species can be attributed to climate change. And the evidence for this is just going stronger and stronger over the years. And we're particularly now able to say with more confidence about the effect of extreme events. We can see that droughts and floods are becoming more frequent in many places as a result of climate change. And we can start to attribute changes in the biodiversity and ecosystems to that as a cause, and hence back to climate change. And that's something which really has changed in the last few years, the role of extreme events. Approximately half of species that have been assessed globally have shifted their ranges to higher latitudes or elevations. That's one of the things that's been known for some time, but the pattern just gets clearer and clearer as species track the distribution of their climate niche as it moves towards the poles and up mountains. We're also seeing shifts in biomes, the actual structure of ecosystems. And I've got a slide on that in a moment, so I'll talk through that then. And we're starting to see evidence of global extinctions or near extinctions. Global extinctions, probably 3 cases that we have some confidence in. But nevertheless, there's an awful lot more local population extinctions that have been caused by climate. And something like 47% of these local extinctions studied, we can see a correlation there. So there's really quite a picture of change happening now. If you look back to earlier IPCC reports, there's a big emphasis on projections, what might happen in future. And we still have that, but we're seeing a lot more about what is happening now. I mentioned about changes in biomes, which really reflects a change in functional types. So this is the sort of situation where tropical forest at its boundary with the savanna may change, or where the boreal forest extends into tundra going north. And each of these little symbols on the graph there, on the map, shows where there's a documented case of that biome level change in the functional type of plants that's actually been detected on the ground. But that raises the question, how do we know? How do we know that's caused by climate change? And this is a detailed table that you're not going to be able to adequately read, but this is all about the evidence base and our confidence in some of these statements about changes in aspects of ecosystems and biodiversity and observed impacts. And I've included it here because if you look at the sort of little symbols just along the top there, it shows you the different type of data that have gone into our being able to justify some of these statements. And I just wanted to draw your attention to 2 of the symbols. One is experiment, which is a little sort of flask here, a lab flask, although actually a lot of these experiments were field experiments. And also this telescope, which is long-term observations. I didn't come up with the symbols, I should say. But basically, this is a table that sets out a statement, so in this case, half of all species where land use change has been minimal have shifted their ranges. And it goes through and it says what the scale is, what the period is, and then the lines of evidence, and finally how confident we are. So if there's lots of evidence, it's robust evidence. If it all says much the same thing, it's high agreement. And if overall, therefore, we have high confidence, we say so. And if we go through that table, you'll find there are 22 confidence statements. All 22 draw on long-term studies. We would not, and it's kind of obvious, but we wouldn't be able to detect impacts at all if there had not been long-term study of some sort, either monitoring or repeat survey. But it's also interesting in this context that 11 of those statements also draw upon experiments of some sort or another. And the thing is, to understand, and this is really preaching to the converted to this audience, I suspect, but to understand why a system changes, you need a range of different lines of evidence, of which the best, I would argue, is actually doing an experiment where you can to test cause and effect. It's not the only way of doing it. There's also a process understanding in terms of physiology and ecology. There's also, numerous complicated statistical analyses you can do. But nevertheless, long-term studies and long-term experiments are really central to being able to make these sort of really very important high-level statements. And just briefly to think about climate change experiments, and I was just flicking through my slides earlier, and I came across this one of Buxton and the late great Phil Grime, both sight and the man well known to many people on this call, I know, the longest running climate change experiment in the UK, not in the world, but in the UK for sure. And we know that's really helped to understand some of the mechanisms of change. My own background in this was a similar experiment at Wytham, which I mentioned at the beginning. We were able to find something about what sort of species did well under drought conditions, and then actually to be able to compare that with what happened during a natural drought to explain that. So we've established that understanding impacts needs long-term observations, and long-term experiments in many cases are critical. But let's leave that aside for a while and look ahead. Because to assess risk, you need a different sort of evidence in addition, and this is where some of the modelling comes in, and to project changes. And we were able to see the evidence base can, as we'd expect, is that the more the climate will change in future, whether to 1.5 degrees of global warming, as on the left of this slide, or rather higher, and it's 3 degrees on the right, there will be a loss at a local scale of biodiversity as well as globally. And you can see on the 3-degree level of warming, some areas, which is those marked red, are looking at potentially losing 75% or more of the species that are currently there in an area. So the picture is really quite alarming. And if we summarize that in these sometimes called burning ember diagrams, we can see that across a whole range of terrestrial, freshwater, and marine also ecosystems, you can see the risks just increase as the temperature goes up. So if we just look at the bar on the left here, it's overall terrestrial and freshwater biodiversity loss, and the higher you go up the bar, the more that corresponds with a rising global temperature. And we're currently about the level where it's sort of greyed out around about here, just above 1 degree. And you can see, you're just at the early stages in terms of impact, in terms of the amount of colour. By the time we get to 1.5 degrees, we're picking up rather more, and it just gets worse the higher you go. Just to bring that down to the England level, some of my work, I suppose from my day job, if you like, with Natural England, and this is work particularly done by my colleague Simon Duffield, or led by Simon, work with some of our National Nature Reserve managers to assess risks to biodiversity on their sites. And this shows the risks that were assessed for biodiversity features on National Nature Reserves from climate change. Feature, could be a species, could be a habitat, but it's the things those reserves were designated for. And you can see red is high risk, amber, as you might guess, is medium risk, and green is low risk. And you can see that at most different types of sites, and this shows coastal, freshwater, grassland, and so on, different types of habitats, for most types of habitats, in fact, for all types of habitats, more than half of the biodiversity features are medium or high risk from climate change. And in some cases, like wetlands and uplands, there's very little that's only at low risk from climate change. So the risk ahead is considerable. And that begs the question then, well, what are we going to do about it? And the first line of approach is, how can we adapt? Adaptation is all about reducing risks. And there is a growing evidence base picked up in our IPCC report around what sort of measures reduce risks to biodiversity and ecosystems from climate change. And these are a number of ones where we had medium or high confidence. Things like protecting large areas of semi-natural habitat, adjusting conservation strategies to actually deal with it, protecting microclimatic refugia, places where the risks are less severe. And a number of others. So there isn't really time to go into the detail of it, but there are things that we can do to adapt to climate change to reduce risks. And there's a number of others where the evidence is not so strong at this stage, including, I'll just highlight this one, three out from the bottom, assisted translocalization and migration of species, helping species to move to new places. There hasn't been a lot of work done on that, but it's actually testing that out as a concept, but it's quite often quoted. And that's my segue into a reference to long-term experiments and field experiments. And some years ago, colleagues from Natural England, together with the other country agencies in NatureScot and Natural Resources Wales, went on a field trip to Scotland, and we were taken out into the field by Rob Brooker and colleagues who had actually been trialling translocation of this lichen species to see whether it will grow in places you might expect it to based on its climatic niche. But that's a relatively rare example, and I'd suggest it's something which there's a lot more scope to do more experiments on, testing the effectiveness of translocation and a number of other potential climate change adaptation measures. And so a sort of direction for future travel with long-term field experimentation. Which also recognise the importance of using the natural environment to help reduce risks to people. And there's a lot of interest at the moment in what's sometimes called nature-based solutions, or in the specific case of adaptation, ecosystem-based adaptation. You can view ecosystem-based adaptation as a subset of nature-based solutions, which includes tackling a wide range of other challenges. So there is increasing evidence now that you can use these techniques to reduce the risk to people. For example, natural flood management, particularly good example, but also urban cooling, more green space in towns, and measures you can take to reduce wildfire risk. But it needs to be done well, and there is unfortunately a track record of people not always doing things in ways that actually do reduce risks, and actually sometimes creating more problems. So it's important both to have excellent science, but also really good local knowledge and working in an inclusive way with people in the area. And the final point on that slide is just noting that a lot of these approaches, although they're good, will themselves be a threat as the climate changes. So it's important to understand and reduce that risk. Just an example of a couple of rivers and streams in the Lake District near Thirlmere and Haweswater catchments where this is happening on land owned by United Utilities, and in the case on the left, managed by the RSPB, where they've actually been renaturalising watercourses and allowing natural flooding to happen in sensible places, if you like, within the catchment, rather than downstream causing more problems. I've mentioned it already, but yes, there are limits to adaptation. We can reduce risks, but we can't eliminate them. And that challenge becomes greater the higher the temperature gets. In terms of the evidence base, so I did want to highlight one of these statements that There have been many adaptation plans developed, many strategies, many of them highly theoretical, but there's very little evaluation of the effectiveness of those plans, whether they've actually happened and whether they've done what they've said. So I put up a picture of our own Natural England Climate Change Risk Assessment and Adaptation Plan, published last year, and it's certainly a priority for me to make sure we do monitor and evaluate whether we're doing the adaptation we need and whether it's effective or not. I can talk about that if you like as we go on. I want to change gear though, and this is a whistle-stop tour of a lot of ground, and think a little bit about climate change mitigation. In climate change speak, mitigation is about reducing emissions or promoting sequestration. So it's tackling the root cause, reducing net emissions. And if we look at the global carbon cycle, and this is a picture from Friedling-Stein et al. That I like, there is actually a slightly updated one published just a month or so ago, but the main thrust of it's the same. This shows the global carbon cycle and the role of different fluxes and stocks within it. And I'm just going to zoom in on this element here, and this shows how much carbon is stored in soils, permafrost, and compare that with what there is in fossil fuel reserves, unexploited oil and coal. And it's just to highlight, actually, there is more carbon in the world's ecosystems than there is in fossil fuel. And it's in everyone's interest that it stays there. Those threats that climate change poses to ecosystems is a big threat to the stability of those stocks. Include vegetation in that as well. And deforestation is one of the major causes of emissions at the moment. If we step up and look at the fluxes, these big arrows along the top indicate the different relative size of fluxes to or from the atmosphere. So the big grey one on the left over here is fossil fuel burning. And then the next one here in the circle is the interaction with the land. So the little sort of brownish orangish bar shows the emissions from land use change. Say deforestation is a large element of that, but could also be degradation of peatlands, for example. And then a rather larger arrow, which is the terrestrial carbon sink. It's the removal of carbon from the atmosphere. And there's a similar, slightly smaller, but still significant sink to the ocean as well. And you can see at the moment, roughly half of them, slightly more, I think, of fossil fuel emissions are currently being taken up by natural ecosystems. But that could all change. And there is a real risk of carbon cycle feedbacks from climate change and things like increases in wildfire and tree mortality, and a risk of tipping points where, for example, tropical forest turns into a more degraded savanna state. So that's the big picture. That's why ecosystems matter to that global carbon balance picture. We go and have a look in the UK. We've looked in a bit more detail at our habitats, our ecosystems. And this was a review published last year, led by my colleague Ruth Gregg. And we were able to take an overview from the literature about how much carbon is stored in different habitats. There's a whole talk in this diagram, but just to spare you the details, the bottom line is the largest stocks of carbon in UK habitats is in peat, and that's where these big bars are in the middle. And the next largest store is in woodland, both in the trees and in the soil. But peatlands where the big elements are. If we look though at the carbon sequestration rates or carbon flux rates, within the scientific literature. You'll find if you look at the bottom, the biggest emissions are from peat. So we've got a lot of carbon in peat, but very high greenhouse gas emissions coming from them because of the degraded state. Flip side of that is with woodland at the top, which is the largest sequestration rates. They're a negative term because it's about removal from the atmosphere when expressed that way. And you can see that that's where the largest bars are indicating the highest sequestration rates. And various other habitats, including, for example, salt marsh, are also good carbon sinks too. And that took a lot of work to pull together those two figures. You wouldn't believe how many different units and different approaches different people have taken across the habitats. And it is a report that a lot of people have found very useful for us, having put that on a comparable basis. And there is a message there, I think, about how actually by working together as a community, we can get a lot more information out if we work in a collaborative way and try and express things in a consistent way across different habitats. So we derived a number of key principles from that work. So protect and restore peatlands, create new native broadleaf woodlands. It's very much from the point of view of natural habitats and biodiversity. It's not to say that production forests for timber aren't also important. Of course they are. Protecting and restoring natural coastal processes on which habitats like salt marsh and seagrass depend. But there's also a more general point about the value of semi-natural habitats and protecting them. And so we go on into some of the more sort of targeted response measures around targeting incentives to do the right thing in the right place. Make sure your nature-based solution is where it can have most value. And then also in a busy landscape like ours, integrating those solutions into a climate, into landscapes where agriculture and production forestry take place as well. And then as we get towards the bottom, carry out research and monitoring to fill evidence gaps. And of course, that's ECT's raison d'etre. And then ensure that we take a joined up approach to mitigation and adaptation. So we solutions for climate change are robust in a changing climate. So I could talk a lot about the different detailed studies that might support those initiatives, but I want to think a little bit more generally about evidence requirements. What do we need to know to be able to deliver nature-based solutions for climate change mitigation? And there's some pretty straightforward evidence requirements. How much carbon is stored by different habitats? We've provided an overview, but it was also pretty clear there's a lot of big gaps, and we've lumped in together a lot of different types of grassland, for example. There's a huge range of variation within grasslands. Same is also true of woodlands and every other habitat. And similarly, what are the fluxes of greenhouse gases? How do they vary between habitats? Really critically, how does management affect carbon storage and greenhouse gas fluxes? What can we do to make a habitat store more carbon or to reduce emissions? And how do those different approaches affect biodiversity and ecosystem services? And there's a big challenge at the moment with things like creating more woodland. I was actually in the House of Commons in the Environmental Audit Committee 2 days ago, contributing to an inquiry they're doing into expanding UK timber supply. But what effect will that have on biodiversity? Can we do it in ways which support it, or is it a trade-off? And finally, how does carbon storage, biodiversity and other services change over time? So if we think then a little bit about the sort of long-term ecological experiments that ECT focuses on, bear in mind, I was one of the founders of ECT, so I'm absolutely committed to their value. you can see there is a real role for making gas exchange measurements on different conditions of climate or CO2. Particularly thinking of BIFOR actually, and that big forest scale manipulation of CO2. Changes in soil chemistry, including the stock of carbon itself, and the effects of management too. What I would say though is, whereas these plots are very good for doing things like manipulating grazing as a management tool, it's rather harder with some of the larger scale things like hydrology that tends to operate at a much larger scale. So I think they're necessary, but they're not sufficient by themselves. If we go back to that original thought that different lines of evidence really matter to getting a robust evidence base. And so in the last few minutes, I just want to introduce you what some of my current work is in the English context, which I suppose takes a lot of the philosophy of long-term field experiments, but puts it in a bigger scale, I like to think. So this is a project that we currently working on called Nature-Based Solutions to Climate Change at the Landscape Scale. And this was funded by the UK Treasury, and it's sponsored by two government departments, DEFRA on the Environment, Food and Rural Affairs side, and BEIS, which leads on climate change. And Natural England's leading that, but we're working with partners at Kew, particularly their Wakehurst site, the Environment Agency and the Forestry Commission. And it's big, 12.5 million. And as part of that, we're establishing pilot sites, so places where habitat is being created, which we would expect to be beneficial, particularly contributing to net zero, so climate change mitigation. And what I think is the really critical thing here is that we're combining that habitat creation and restoration with research. So it's a pilot, it's all about learning. And I'd like to see a lot more of that approach, learning by doing, if you like. So taking a scientific approach to environmental management. Also running alongside the science and the habitat creation, there's also a lot of work going on about green finance. So can we bring in additional sources of funding for those sites, based perhaps on private sector funding, including for carbon offsetting? But that's something which really has to be done well, and that needs that good evidence base that we're developing. So just to tell you a bit more about the science side of it, which I lead. So we are aiming to establish baseline carbon fluxes and storage and some of the initial changes on the pilot sites. It's not a long-term project. We're going to have to do a lot of work in the coming year and a bit to get that baseline. We're then looking to keep that going into the future, coming back to see how things change over time. If we create a new grassland or a new woodland, how's the carbon build up over time? But because we don't have time to wait, really, we're also using a more retrospective approach, a chronosequence approach. So looking back at habitats created over the last few decades to see how carbon has built up, using a sometimes called a space for time substitution. That has its limitations, which is why we're trying to start by getting a baseline on these new sites. But it's still a big use for it at the moment. And we'll monitor carbon, both in terms of flux, but also the stock of carbon. And at the same time, look at biodiversity and some of the other benefits or disbenefits of those actions. Just a couple of slides to show we're doing this from last summer at Parsonage Down. Some of you know. Not probably what most people would think of, but it's the most likely candidate for being a carbon sink. It's very thin soil on chalk, but actually there is more carbon in the older grasslands. I can say that with some confidence now. And so, you know, even a relatively low carbon ecosystem can build up carbon over time and play a role. So I'll I'll finish there with a few conclusions. First of all, it's clear ecosystems are critical to tackling climate change. The carbon that's in them needs to stay there and be increased. But it's also essential to tackle climate change itself, to protect ecosystems and the services they provide to people. The threat is real, immediate. Multiple lines of evidence are required for a good understanding and decision making. It's not monitoring versus modelling. It's not about field experiments versus process studies. We need all of it. And the evidence is so much more powerful when different multiple lines of evidence point the same way and support each other. So long-term monitoring and experimentation are a critical part of that evidence base. But I contend that while pilot-scale field experiments still have value, and a lot of value, they're not sufficient by themselves, and we need to evaluate, well, we need to pilot and evaluate climate change adaptation and mitigation techniques as a landscape and catchment scale as well. That is my last slide. So I think we can probably move to some questions.